Good afternoon and welcome to UniCourse and Unit 13, which is on fundamentals of thermodynamics and heat engines. And in this session, we're going to look at the preparation for assignment number 3. So first of all, just so we're clear what we have to do, we'll have a quick look at the assessment criteria. So we'll start off, there's 4 criteria. So first of all, P6, which is to determine the heat transfer through a composite wall, and that's addressed in task number 1. Then we'll look to apply heat transfer formula to heat exchangers, and that's again addressed by task 2. The third criteria is to explore heat loss through lagged and unlagged pipes. Again, that's in task 3. And the final criteria is to distinguish the difference between parallel and counterflow recuperator heat exchangers. And that's adequately addressed in task number 4. So in this presentation, well, first of all, we're going to review task 1, and we're going to look at the associated theory. Then we'll move on to the approach to completing task 2. So there's no theory involved in preparing you for that assignment. And then we'll look at task 3. And again, we're going to look at the associated theory. And task 3, if you can remember, is to do with heat loss in pipes, lagged and unlagged. So the formula derivation needs to be done so you understand where the equation that we're going to use has come from. And the last task, which is task 4, we're going to look at the approach to completing task 4. So we're not going to do any sort of theory associated with that, but we'll give you pointers in the right direction. And hopefully by the end of the session, you should be in a good position to have a good crack at this assignment. So let's start off with task 1. So that's probably the best place to start, isn't it? So we've got a 4 meter high by 25 meter wall, which is composed of 2 bricks of length 0.1 with an air gap, with a gap in between them of 0.05 meters. And we're given the temperature inside the room is 25 degrees C, and the temperature outside of the house is 5 degrees C. So we're asked to determine the heat transfer through the wall when A, the gap is filled with cotton wool insulation, and B, which is most probable, the gap is filled with foam insulation. Now below, you're given all the requirements in terms of thermal conductivity for the brick, for the cotton wool, for the insulation, and you're also given the convective heat transfer coefficient for the inner wall and the outer wall of the building. So the approach to this, you should always start off with a sketch to draw the system. So what we have here, we have the brick. So we have the brick there, and we have the outside brick. We have the inside temperature, which is given at 25, and the outside temperature at 5 degrees C. We're given a thermal conductivity for the brick. So that, write it down on the sketch. So if you don't, what happens if you don't do this? You're likely to get the numbers mixed up. So trying to do it by just looking at the text in the question, you'll probably pick up the wrong value. So your answer will be incorrect. Okay, that's not the end of the world. However, when we look at the question, you'd expect to see an answer that is going to give a difference. If we look at the insulation, the thermal conductivity of the insulation is higher. So that is higher than that of the cotton wool. So we'd expect a higher heat transfer. So if we put the wrong numbers in there somewhere, we might not get the expected answer, and it might be difficult to understand where we've gone wrong with our solution. So it's a good idea, sketch the question out and put the values on that sketch from the question. So again, we've got the thermal conductivity of the outer brick, and I've shown here the thermal conductivity of the insulation. And for this one, I've chosen the cotton wool, but in the second part, in part B, you'll have to change that to the thermal insulation of the foam. We also added the convective heat transfer coefficient on the inner surface and the outer surface. So we've got all the information that we need now to determine the heat transfer in this direction through that system to the outside wall. We'll just go back onto the previous slide. So Q, you're going to be going in that direction, and I'm going to call that Q. Q, the heat transfer, Q dot means it's a rate of heat energy flow, and it's in watts, which is joules per second of energy flow. So to do that, let's look at the theory first of all, and we'll come up with the equation that will help us solve that problem. So I'm going to go back maybe to the workbook, and you'll see this equation in the workbook. It's called Fourier's law, where the heat transfer Q through the system, which we've just shown to you, is given by the thermal conductivity times the surface area, which is at right angles to the flow. So Q will be at right angles to the surface of the fluid, so that will be Q through our system. We have a temperature gradient, so theta is the temperature, so we have a temperature at the inside, and we have a temperature on the outside. We have a distance x, which happens to be the thickness of the wall, so we have our value x, which is the thickness of the wall. We also have the surface area through which the heat is going to move, is going to be transferred, and that's a surface that's normal to the direction of flow of the heat energy. So that's in meters squared. d theta by dx is the thermal gradient or the temperature gradient. And if we look at any system, so we've got a one piece system, only one material, we've got a temperature theta 1 on the inside, temperature theta 2 on the outside, and it's got a thickness x. So the temperature gradient d theta by dx is simply theta 2 minus theta 1 over our thickness, which is x. Right, what we're going to do now, we're going to take Fourier's equation, Fourier's law, and we're going to integrate with respect to x, and we're going to assume that k, a, and q dot are constants. So if we do that, then we can take the x over to the other side. So we're going to move this dx over to the other side there. So we get q integral of 1, essentially, dx is equal to minus ka, and the integral of 1 d theta, again, between theta 1 and theta 2. Now, if we integrate that, we get q dot x is equal to minus ka theta 2 minus theta 1. So you've done that in unit 2. That's a fairly straightforward integration. We can rearrange that. I'm going to tidy it up a little bit. So q is now equal to ka theta 1 minus theta 2 divided by x. So that's quite a neat equation. We could apply that to solving our value of q, but what we want to generate is an equation that can be used for multiple surfaces and multiple materials. So we're okay with that equation so far, but we're just going to derive it, just tidy it up a little bit more so we can use it as a generalized equation. Right, first of all, carrying that equation over from the previous page, so that's the equation on the top right, and we can rearrange that equation to q is equal to theta minus theta 1 minus theta 2 divided by x over k times a. So that's just rearranging that previous equation. So I want you to bear that equation in mind. So we'll put a tick by that to say we've discussed that. Now we're going to look at an electrical circuit and look at the analogy with an electrical system. So you're probably familiar with Ohm's law, where V is equal to IR, but we can rearrange that to I is equal to V over R. And you'll see there's some analogy there. I could be Q, V is the potential difference, the voltage difference, or temperature difference in this case, and we have resistance here, R, in our Ohm's law, which is similar to the resistance of the thermal system. But it's not just a single value. The thermal resistance is X over KR. So the words underneath explain that the current is analogous to the energy, the heat flow Q, heat transfer, and the thermal resistance is an analogy to the resistance of the system. So don't forget, if it's a resistances that are in series to each other, you can simply add them up. Now that's important to remember that. So if you've got a system with a number of resistances in series with each other, you can just add them up to get the total resistance. Now you can do exactly the same with a thermal system. So you can simply add up the thermal resistances that make up your system that you're trying to analyze. So let's go over onto the next page. So this is a bit busy. There's a lot of information on this page, but don't worry about that at the moment. So we've got three materials, 1, 2, and 3. And we've got a temperature at the inner surface, θ1, then at the interface, θ2, second interface, θ3, and the outer surface, we call it θ4. Now, if we will look at an electrical circuit, now you remember that if you have resistances in series, that the current through all those resistances is going to be the same. And there'll be a voltage drop across each resistance. So if we wanted to know what the total current was flowing through that electrical system, I would be simply equal to the potential difference V1 minus V4 divided by the sum of the resistances, which is R1 plus R2 plus R3. And I'm sure you're all familiar with adding up resistances in parallel and working out the current. But we can use the same now for thermal transfer, thermal energy transfer, heat transfer through a system. So if we've got multiple materials, so maybe it's like the question, we've got a wall of a house where we've got brick, we've got a brick here, we've got some sort of insulation, and we've got another brick, then we can simply add up the thermal resistances. And we know the thermal resistance is given by the thickness of the particular material divided by its thermal conductivity times the area. So like the electrical system, if we want to know what Q is simply, given we go over the other side to the left-hand side of the page, Q is simply the temperature difference over the whole system, which is θ1 minus θ4, and that's divided by the sum of the thermal resistances for material 1, material 2, and material 3. Now we can tidy that equation up a little bit because each term we assume that the area is going to be the same. It's not for where we have circular geometry, such as we're going to discuss later in pipes, but for a flat surface, the surface area will be the same. So we can take the area out of that expression and take it outside of the brackets. So we have Q now is equal to θ1 minus θ4 over 1 over A. And we have X over K1 plus X over K2 plus X over K3. And of course, K is the thermal conductivity of each material, and X is the thickness of each material. You can see how we're actually now progressing towards the solution to assignment to the first question on task 1. So rather than expressing this equation in that form, we can generalize the form a little bit, where Q is equal to θ1 minus θn plus 1, where n's the number of materials we have. So that's why if n is 3, we have in our example, then n plus 1, that would be θ4, wouldn't it, as we have in this example here that we've already done. So to bear in mind is that for flat material, and we're looking at heat transfer through that material, that the thermal resistance is given by this expression here. So it's important to remember that. So that's the thermal resistance when we're discussing conductivity through those particular materials, conduction through those materials. Right. One thing we can do, which is very useful to us, particularly if we're looking at the interface temperatures, again, treating it as an electrical system. So if we wanted to find our value of V2 on this electrical system, well, we know resistance 1, we know the current, we've already established the current. So if we look at the current now, we know the current, we look at V1 and V2 is trying to find, and the only resistance we have there is R1 in this case. So that allows us to calculate V1, which would be the voltage between resistance 1 and resistance 2. We could take exactly the same approach if we're going to find the temperature at the interface between material 1 and material 2. So theta 2 in this case, we're finding the temperature at that interface. So to do that, we simply say Q is equal to theta 1 minus theta 2. So temperature difference across material 1. And we're going to divide by the thermal resistance of material 1, which is xk times A for material 1. And from that, we can establish we have Q, we have the heat flow, we have theta 1, we don't have theta 2, so we have the thermal resistance. So that allows us to determine the interface temperature. Now that's sometimes important, especially if you're looking at heat loss through pipes, because you want to know what the interface temperature is where you start the insulation to make sure the insulation isn't too hot, that the insulation might be too hot at the interface point and could damage it. So you've got to be careful that you know what the interface temperature is on occasions. Right, there's one more term that we've got to add to this expression. We've looked at conduction through those slabs. Now we've got to look at convection away from the outer surface. So it's all well and good that we're saying, right, we've got heat flow through that system. Draw this Q. But there's two mechanisms. The heat transfer will be by conduction through the material. So it'll be conduction there, conduction there, and it'll be by conduction to the final material. But away from the surfaces, you have convection taking place. So there'll be a temperature gradient at the surface due to convection. So typically it'll look like that on the inlet, and on the outlet, it'll look something like that, the temperature gradients at the inlet and outlet. So we can't ignore convection away from the surfaces because it does happen. Now, saying that, on task 4, we are ignoring convection because it's quite difficult to deal with in that terms. So we'll discuss convection from a circuit, from a pipe a bit later on. Well, let's carry on with convection so that we have an understanding of it. So we're now talking about convection away from the solid surface into the bulk of the fluid. So there's a temperature gradient there. Now, given the temperature gradient, typical temperature gradient, where theta F1 is the bulk mean temperature of the fluid, so away from the surface that we're trying to investigate. The heat transferred by convection, Q, is equal to something called H, we'll discuss H in a minute, times the area, times the temperature difference between the surface and the bulk mean temperature of the fluid. We can rearrange that equation, so we get Q is equal to theta 1 minus theta F1 divided by 1 over H times A. Now, hopefully you can see where we're starting to go. That's the same format as conduction. We have the temperature difference at the top, and we have something called the thermal resistance at the bottom. So when we're dealing with convection, the thermal resistance is given by 1 over H times A. Now, what's H? We need to establish that, don't we? Well, H is the surface heat transfer coefficient, or the convective heat transfer coefficient, or whatever we want to call it. It's given in watts per meter squared K, and it's very dependent on the surface that the convection fluid and whether it's free or natural convection. So this term H for the convective heat transfer coefficient is dependent on many, many variables. It's dependent on the temperature difference, it's dependent on the density, it's dependent on the viscosity of the fluid. So establishing the value of H is extremely complex and fairly long-winded because there's so many variables in determining that value of H. So you can imagine if there's no draft then you'd have a different profile. But if you had air blowing along there, that temperature profile would be much different and the value of H would be much different. So you've got to be wary of this value of H on how you apply it to a particular problem. But anyway, for our questions, we're going to give you the value of H. So what we've got to do now, we're going to look at our system. So again, we've got 3 materials. So there's material 1, 2, and 3. And we know that for the thermal resistance, it's 1 over A times the sum of X over K for each material. We've got to do exactly the same for the convective components, which is also the thermal resistance. And because they are in series with each other, then we simply add it on to the conduction thermal resistance. So we've got 2 components in the thermal resistance now. So if we look at the thermal resistance, this is the thermal resistance at the bottom for this system shown on the right. So Q is through that system. So we have convection at the inner surface, and we have convection at the outer surface, and we have conduction, conduction, and conduction through the solid material. If we look at any situation, we can have any number of materials, solid materials, but quite often we only have an inner and an outer convective component. So in our system here, we've got 3 solid materials. So we'd expect to be a thermal resistance to be made up of 3 components. And then for the convective components of thermal resistance, we would only have 2 components in that. So we'll go over now onto the next slide and hopefully, before we do that, let's just go back onto this one. So the equation you need to apply to solve the task 1 would be this expression here. So this is the expression, the equation you need to use to solve task 1, where theta F1 is the temperature of the fluid inside the room, theta F2 is the temperature outside the room, and then you've got the material, you've got X for the bricks, so there'll be 2 components for the solids. There'll also be another component of conduction for the cotton wool or the foam, depending which one you're doing. And you'll also have a convective thermal resistance, which with this corresponding value of H for the inner and outer surface. So hopefully you can see by applying that equation, you'll have 3 components in there. So you'll have brick plus insulation plus another brick the outside. And for the convective components, you'll simply have the inside convective thermal resistance, so just the inside and the outside convective components. Yeah, so you'll have 5 terms at the bottom of that equation. Now, there is a similar example in the workbook which you can have a look at. Right, let's move on to task number 2. So we're taking a little bit of time here, so we don't want to rush through this. So task 2, a heat exchanger is using steam flowing at 4 kilograms a second and 300 degrees C to heat water flowing at 1.3 kilograms a second from 15 degrees C to 80 degrees C. So you've got the temperature difference from the water. Assuming a specific heat of water and steam are given as 4.187 and 1.996, calculate the heat transfer rate and the exit temperature of the steam. Now, we're not going to do the theory on this, but we'll explain, try and push you in the right direction to get you started. So the first thing we've got to think about is that we assume there are no losses. So this could be any heat exchanger. I know I've shown a counterflow, parallel flow heat exchanger with a counterflow direction. So we'll assume there's no transfer losses out. So there's no Q from the casing, and so that's equal to 0. So if that's the case, then the first law of thermodynamics requires that the rate of heat transfer from the hot fluid be equal to the rate of heat transfer to the cold fluid. So that means the energy given up by the hot fluid must equal the energy gained by the cold fluid. And we're looking at heat transfer, energy transfer in the form of heat. So if we look at the energy given up by the cold fluid, it's simply Q is equal to the mass flow of the cold fluid times its specific heat times the temperature difference of the cold fluid minus the cold fluid in, the temperatures. So that will give you the heat transfer rate Q. Now we've said the first law of thermodynamics requires that the heat transfer from the hot fluid to the cold fluid must be the same. So for the hot fluid, Q is equal, again, to the mass flow of the hot fluid times its specific heat times the temperature difference between the inlet and the outlet. Because that's the case, then these two equations are going to be equal to each other. So the way to answer this question is, 1, determine Q. Q for the cold fluid, because you know the temperature in and you know the temperature out. You've got the mass flow, so you've got mass flow, you've got specific heat, you've got the temperature difference, so you can get Q. And then you can use that value of Q in the second equation there, because you'll have the mass flow for the hot fluid, the steam, you have its specific heat, and you have the temperature in, which is 300 degrees. So that allows you to calculate the out temperature. So again, look at your answer when you've got the answer to see if it's sensible. Is it lower than the inlet temperature? Then you know at least you've gone the right way. So if the steam is the heating fluid, it goes in at 300 degrees, you would expect it to come out at a lower temperature, like you would expect the hot water, the cold water to be heated up from the inlet temperature of 15 to the outlet temperature. So I'm not going to say any more about task 2. I think that's relatively straightforward. Please, if you are having difficulty with any of these, please don't hesitate and get in touch with me so we can have a discussion with it. Send me an email and a number and your availability, and I'll ring you back. So please do that. Right, task 3. This is a little bit more fiddly. So what we've done on this question is that we've ignored the convection component of heat transfer. So we're only looking at the conductive heat transfer through the solid materials. So it's split into 2 parts. So task 3, part 1. So we've got a 2-meter copper pipe with an overall diameter of 30 millimeters. Has a wall thickness of 6 millimeters, and it's moving water at 70 degrees C. So that's the internal temperature of the pipe. The outside temperature of the room is 30 degrees, and the thermal conductivity of the pipe is given as 401 watts per meter K. So calculate the rate of heat loss. Okay, that's fairly straightforward, isn't it? Once you've done that, we're going to insulate the pipe. So the pipe in task 3, part 1 is now going to be covered with insulation, and it's got a thermal conductivity of 0.055 watts per meter K. So now we're going to calculate the temperature at the outer surface of the copper pipe. Right, so what equations are we going to use? Let's have a look. So again, we're going to start off, we're going to look at conduction. We're not looking at convection this time. So one thing we have to assume is the temperature that we're given for the outside is the same as the surface temperature of the outside of the pipe, and the temperature that we're given for what's inside the pipe is equal to the surface temperature at the inside of the pipe. So again, we're going to start off with Fourier's law, and we're not going to go over that again, but the only difference is this time, the area is not a flat panel, so the area is the circumference, which is 2 pi r, times the length of the pipe. So that's our area of pipe. So what we're going to do now, we're going to insert the area into our Fourier's equation. So Q becomes minus K 2 pi RL d theta by dr. Now we're going to integrate that. So what that means is what we're going to assume again that Q, K, and L are constant. But this time we're going to rearrange it. We're going to take R to the other side of the equation. So we'll take R to the other side of the equation. So it becomes 1 over R dr, and we have d theta left on the right-hand side of the equation. So now we're going to integrate 1 over R dr between R1 and R2. Now, if you can remember from Unit 2, 1 over R, the integral of that is log of R, and because we're doing between R1 and R2, it becomes log of R2 divided by R1. Just to remind you of the mathematics. And that's equal to minus K 2 pi L and theta 2 minus theta 1. Now we can get rid of the minus sign by simply switching theta 1 and theta 2. So we have theta 1 minus theta 2. So that gets rid of that negative. Why the screen went blank then. So we're going to tidy up that equation now. So Q, having taken Q as out of the expression, making it what we need to establish. So it becomes 2 pi KL theta 1 minus theta 2 divided by log of R2 over R1. And just a little bit further tidying up, we have theta 1 minus theta 2 on the top. And on the bottom, we have 1 over 2 pi KL times the log of R2 over R1. Now, this is the bit to remember. This is now the thermal resistance if you have a geometry such as a cylinder or a pipe. And that's because the area changes as you move away from the center. So as you go through the material, so as Q goes in this direction, what you'll find is, of course, is that the area is increasing. So the thermal resistance is more complex, and we've now established what the thermal resistance is. So now what we've got to do is think about this situation if we have a composite pipe, which is a copper pipe with some insulation on it. Just before we do that, we'll put this equation in its general form. So we've established the thermal resistance from the previous slide. So we can add the thermal resistances. So in its general form, Q is the overall temperature difference, and that's divided by the overall thermal resistance. So it's 1 over 2 pi L, and it's the sum of the log of the different radii divided by the respective thermal conductivity for the particular material we're looking at. Now we'll talk about that on the next slide. Hopefully that will become a bit clearer. So if we now look at our pipe, this is our pipe shown in red. That's the copper. And we've got the insulation. So that's the insulation on the outside in grey. And this time we've got R1, R2 for the copper, and we've got R3 now for the insulation. If we look at our equation, what we have to do is we have 1 over 2 pi L, and we need to add the thermal resistances for each component. So for the copper pipe, that would be the thermal resistance, and for the insulation, that would be the thermal resistance. And because they're in series, we can just simply add them up. So this is the equation that you would use to determine Q in task 3, part 1. Yeah, so this would be in for task 3, part 1. So I've put a procedure there for addressing this question. So part 1, without insulation, find Q, part 1, using theta 1, theta 2, inside and outside temperatures, we're given those, R1 and R2, being the inside and outside radius of the copper pipe. Now for part 2, you can't do part 2 the question requests you to find, what we have to find is the temperature at that interface there, so it's in red. So that's what we're trying to find, that interface temperature. But before that, we need to find the new value of the heat transfer. Because we put insulation on the outside of the pipe, what's going to happen now, Q is going to drop. We'll have a lower value of Q than we would in part 1, which is what the reason for insulation is anyway. So you've got to find new Q for part 2. This time you're using theta 1, theta 2, R1, R2, and R3, which is equation 1. So I've written that down there. So this is for T3. Oh, screen's gone off again. No, it's come back. Part 2. And this is for task 3, part 1. So we'll just cross that little bit off so it doesn't cause confusion. So they're the 2 versions of the above equation you've got to use. Because remember, in the first bit, it doesn't have any insulation on it, so that term wouldn't exist. So the last bit was to find the outer surface temperature of the copper. So again, doing that, you would simply use the first equation. So you'd use this equation in there to find the surface temperature of the interface theta 2. So that would be a question theta 2 in that case, and you can find theta 2, given now that you would have a lower value of Q with the insulation. So you will find the temperature is actually going to be very, very high. It's going to be very close because it's copper. It's got a very high conductivity. You know, the temperature there will be pretty close to the temperature at the surface of the inner surface. So it's going to be fairly close to that temperature. So I hope that helps you do that question, task 3. And we'll quickly discuss task 4 now. So task 4 is to distinguish the main difference between the performance of a parallel flow and counterflow heat exchanger. So the approach to this question is you have to do some research on this. So there's lots of information available on our website. And I've put a useful source on the bottom there, which is a heat transfer book. It is available online. There's lots of PDF versions of this book. And I think it's sort of chapter 13 of this particular edition. And you'll find a very good explanation and some diagrams in there, which you can use those diagrams by all means. There's no problem with that, as long as you've referenced them. Be careful, make sure you reference where you've got your information from. So how would you answer this question? Well, the first thing would be to sketch the 2 types of heat exchangers. So this, physically, they look very similar, except the flows are in opposite direction. That's the only difference. Then graphically represent the temperature profile of the fluids as they flow through each heat exchanger. And again, we want you to sort of demonstrate the temperature profile. And from that, you'll be able to draw some conclusions. So we'd expect you to comment on the temperature profiles and comment on which configuration has the higher heat transfer rate and why that happens. So that's what we'd expect you to do in answering task 4. I don't want to say any more on that because I think I've probably given you more than I should anyway. Right, so completing the assignment. Include a contents page. Yeah, well, we have to do that. So, it's a report type work. So you've got to say what's in your assignment in case one of the pages goes missing. So say you didn't upload one of the pages and you put in the contents page that you've done tasks 1, 2, 3, and 4, but we can only see number 4. Well, that means we can get back in touch with you and say, look, you've missed a page out here. Can you send it to us now? So, it safeguards you as well. So identify each task either by the letter or the number, so we know exactly which question you're answering, which task you're doing. Type up all written text. So if it's text, type it up. Equations can be handwritten. Make sure they're neat. and you can scan them in. So you can use whatever scanner you've got maybe on your phone, but scan them as a PDF, insert them into your drawing, into your work. As long as they're neat, that's fine. Don't, whatever you do, don't take a photograph, you know, here's a, oh, I've done my equation, I'll take a, I've scratched it out. I'll take a photo with my phone and put it in. That's not acceptable. That's not very professional. So make sure you scan it in and insert it properly. Make it look professional. So it's okay to use images, as I've just said. So you can use images from textbooks, use charts, tables, etc. to support your answer. But don't forget to refer to these in the supporting text. So for example, if you have an image, you need to say what the image is in the supporting text and say, as shown in figure 2, and explain what that image is about. Otherwise, putting an image in with nothing there to support it, it has no value. You may as well not bother putting it in the first place. Yeah, so you've got to say what it's for. And the last thing, not least, to make sure that you're not accused of plagiarism, include accurate citations and referencing. Referencing goes in the list at the end, where you've got the information from, and the reference should include the author, the title of the article, the web address if it's a web source, if it's a book, the publisher, and also the date that you access that information if it's online. Because the reason you put the date on if it's online, because you could go tomorrow and it's gone, or it's changed. So you've got to be careful with web sources. And that's it. Hopefully that's helped you somewhat in preparing for assignment 3 on unit 13 in thermodynamics. Right, thank you very much. Are there any questions?
Yeah, I have a couple, but they're kind of about